Hello everyone. In this video I'm going to be talking about formulas. I know some of you are thinking, well, we talked about formulas in chapter 2. But yes, something you'll realize about chemists is we love to subcategorize everything. So once you think you understand a concept, then just hold on to that belief because later on it's going to come up again in 3 different categories. And so this video is going to be focusing on empirical and molecular formulas. And so a molecular formula is basically what you're used to seeing. A molecular formula tells you the exact number of atoms inside of that molecule or formula unit. And so something like H2O was telling you that you have exactly 2 hydrogen atoms and 1 oxygen atom. While on the other end, empirical formulas are simple whole number ratios of the atoms inside the compound. And so one reason why this actually even matters is important is because if you're working in a lab, all you can really determine is the empirical formula. You can just tell a ratio of hydrogen atoms to oxygen atoms. You can really, without a little bit more information, you can't tell the actual number or how these things are actually doing to one another just doing simple chemical experiments. So, H2O2, this is hydrogen peroxide. This is the molecular formula telling you that there is exactly 2 hydrogen atoms for every 2 oxygen atoms. But when we were looking in the lab and we would do these experiments, we can only determine the simplest whole number relationship between hydrogen and oxygen atoms. Or the empirical formula, if 2 to 2, the simplest whole number ratio between those is 1 to 1, or your empirical formula would be just HO with no of the subscripts there. Similarly, C4H8. So in this case, you're looking at the exact number of carbons and hydrogens in this molecule. But the empirical formula would be a simple ratio 4 to 8 or 1 to 2 carbon to hydrogen ratio, or an empirical formula of CH2. So one thing that should kind of, be obvious here or kind of like painful to look at is in the last chapter I discussed carbon's magical number is 4. It will always, always, always make 4 bonds. And so the empirical formula CH2, that is not telling you that is how that molecule is like put together that way. That CH2 is just saying a simple whole number ratio of 1 carbon to 2 hydrogens exist in that molecule. And the last example I have is something like CCl4. And so in this case, the simplest whole number ratio between 1 to 4 is, 1 to 4. And so every once in a while, you'll come across a molecule like water where the empirical formula and molecular formula just happen to be the same. And so a few things that aren't really specifically pointed out in your book, but you need to keep these in the back of your mind anytime you're dealing with these types of problems, is the empirical formula is only giving you a whole number ratio of just the atoms. It's not giving you the specific number of atoms, nor is it a specific whole number ratio of masses. It is just the atoms. Masses do not come into play here, yet. And so the other thing that is, again, you have to be like practicing at these a little while to get comfortable with the situation. But all molecular formulas and their empirical formulas are tied to one another by a common multiple. And what I mean by that is if you look at the molecular formula of hydrogen peroxide, it is H2O2. But if the empirical formula is HO, so what did you divide both of those subscripts by to go from H2O2 to H1O1? And in this case, you divided it by 2. And so if we kind of go through and look at this previous example here of the C4H8, your N for that one would end up being 4 because you divided the 4 by 4 to get to the C1 and you divided the 8 by 4 to get to the H2. And so every empirical formula, molecular formula is always going to be tied to one another by, again, they don't want to give it a special name. They just say whole number multiple, or we're going to call it N for these future cases. And the last thing is not really particular for empirical formulas. It's actually more important for almost any other type of calculation you're going to do. In masses, masses will lie to you nonstop. For example, if I tell you that I have 10 kilograms of bowling balls and 10 kilograms of grapes, I'm telling you the masses of both of those, but I'm not telling you the actual number of bowling balls and grapes. You should be safe to assume there's a whole buttload more grapes than there are bowling balls, But in this case, masses are very, very misleading. The only thing you can do with masses is convert masses into moles. That's the only way you're going to see some common relationship between all of these. So as I kind of covered in the previous video, you have to be very comfortable with converting anything into moles, especially masses. And so, if we want to calculate these empirical formulas, there are pretty much three, I call them simple steps, but I've been doing this for over 15 years. So there are three steps that you need to be comfortable doing in order to go through these problems quickly. So the first step is figure out the mass. And so sometimes these problems will tell you exactly the number of grams of each of your compounds. Most of the time, though, you're going to be given these types of problems and they're going to be represented in terms of percentages. And so one great thing about percentages, and why I made sure to cover this in my previous video before this video, is mass percent, as I kind of mentioned in the previous video, is mass percent doesn't matter the actual mass. And so a percent is always going to be the same percent for all of these chemical formulas. And so if you are given everything in terms of percent, just assume you have a 100 gram sample. And in that case, 90% of 100 grams is 90 grams. So it saves you a whole lot of headache. And as I mentioned, percents are not going to change regardless of the sample size. And so if you're given percents, erase the percent sign, write a gram sign, you're done with step one. So step two is to convert your grams into moles. And so we know how to do, or you should be comfortable doing this. If you checked out the previous video, then again, you know how to convert mass to moles using the molar mass. And so either I will give you the atomic masses of these complexes, or I will tell you, look at a periodic table. It's on there everywhere. And so once you write these things in terms of moles, you can write down what they call a pseudo formula. So pseudo formula just means it's not quite right, but you're heading in the right direction. And so a pseudo formula is written down because sometimes your subscripts might not be the perfect form that they need to be in. And so if they're not whole numbers, or if they're not in the simplest whole number ratio, you need to just write down a formula to kind of be a placeholder. And then from there, you need to convert your subscripts into values that actually represent simple whole number ratios. And so if they're not the simple whole number ratio, figure out what the simplest ratio would be. If there are decimal places, figure out what you need to do in order to get rid of those decimal places. Remember, these subscripts need to be whole numbers. You cannot have fractions of an atom. For instance, if you were to take a battery, and again, it's going to need to be a little bit more stronger than this ever-ready battery they have in this picture here. But if you were to electrocute water, you can actually decompose water into hydrogen gas and oxygen gas. And in the lab, you can actually collect these gases using these certain absorbers, and you can weigh the masses of oxygen and hydrogen. And while that's all well and good, what do these masses actually tell you? Well, I'll show you. And so say that we electrocute some water and we produce 3 grams of hydrogen and 24 grams of oxygen gas. And so the first thing, as I mentioned, that we need to do is convert our masses into moles. So using the atomic mass of hydrogen is 1.01 grams per mole, and the atomic mass of oxygen is 16.00 grams per mole. We can convert our 3 grams of hydrogen and our 24 grams of oxygen into moles of hydrogen, moles of oxygen. And here, just did math, a little bit of rounding just because I don't want to carry this out to 10 decimal places. And so using my significant figures, my 3.0 has 2 sig figs, the 24 has 2 sig figs, final answers are rounded to 2 sig figs. And so now that we have our values in terms of moles, we use those values as our subscripts in our pseudo formula. And so because I calculated that I have 3.0 moles of hydrogen, my 3 is going to become the subscript for my hydrogen. I calculated I have 1.5 moles of oxygen, so that 1.5 becomes the subscript for the oxygen. And so this is a pseudo formula because hopefully this should be giving you a panic attack just looking at it, because you cannot have half an oxygen. It just doesn't exist. And so the way we kind of figure out the simplest whole number value here is to divide both of those subscripts by the smallest subscript. So between 3 and 1.5, 1.5 is the smallest one. So divide both of those values by 1.5, or 3 divided by 1.5 gives you H2. Your O 1.5 divided by 1.5 gives you 0 or 1. And so your molecular formula here, sorry, not molecular, your empirical formula here is going to be H2O. And so reason why we divide by the smallest subscript. In this case, dividing by the smallest subscript ensures that at least one of your values is going to be 1. And so here it's going to be a lot easier for you to recognize the relationship between 1 and 2 and 1.5 than it would be between like 0.33, 0.66, and 1.22. I'm not even sure if those are right numbers. In this case, divided by the smallest subscript will always give you some value of 1 and help you out a little bit more. So this 3 divided by 1.5, not too complicated. But what if you come across some crazy number like this? And so if you have a pseudo formula that is all decimal places, you end up with, again, something like Zn 0.21, P 0.14, O 0.56. And so if we do the same previous step, divide all of these by the smallest subscript, or that 0.14, I end up with my Zn 1.5, P1, and O4. And so if we rewrite this pseudo subscript again, should still kind of look a little bit funky here. And so the problem now becomes, if we were to divide all of these by the smallest subscript again, we would all divide it by 1. And so 1 will not make a bit of a difference. And so if dividing by the smallest subscript doesn't get you to where you need to be, the next step is going to be to multiply. And so here you need to be familiar with your common multiples. And so if you have something like 0.5, you need to understand that you need to multiply that by 2 to get rid of the 0.5. If you have something like 0.3333, you know, or 1/3, you need to know that multiply it by 3. If it's 0.25, multiply by 4. If it's 0.2, multiply by 5. Those kind of deals. And so here, once you multiply all of these by 2, you end up now with a Zn3P2O8, which in this case looks a lot better than my weird little first pseudo formula I had there. And so this next step is kind of what I was talking about earlier. If you are given the experiment inside of a lab, all you can figure out is the empirical formula. You need to have one additional piece of information if you want to be able to convert that empirical formula to a molecular formula. And the information you need to know is the mass of the molecular formula. And so in the previous steps here and everything that I was kind of showing you up until this slide, we have been talking about the empirical formula. But once you figure out the empirical formula, you can figure out the empirical formula's mass. Once you know the empirical formula's mass, you know that if the formulas are tied by, again, this magical n, then the masses also have to be tied by that magical number n as well. And so if you know H2O2 is the molecular formula, and you know that HO is the empirical formula, you can, again, calculate and figure out the empirical formula has a molar mass of about 17. Or if you look at the H2O2, that has a molecular mass of 34. And so 34 divided by 2 is 17. Your H2O2 divided by 2 gives you the HO. That's all I mean by this magic N. It's going to be the same relationship between your formulas and your masses. So if we put it all together, we can work out this problem right here. And so elemental analysis of lactic acid, and I give you the molar mass is 90.09 grams, shows that this compound contains 40% carbon, 6.7 mass percent hydrogen, and 53.3 mass percent oxygen. I want you to determine the empirical formula and the molecular formula of this lactic acid. And so as I stated previously, in this problem here, we are not given masses, but we are given grams. And so in order to save yourself a whole bunch of headache, don't try to figure out what these percentages of some unknown masses, just figure out 100 grams. And so if we assume that we have 100 grams, then there we can make our 40 mass percent of carbon 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. And so don't worry about it, because 40% of 50 is still going to be the same percent out of 100 out of 17.3. The percents aren't going to change. And so when we kind of go through and look at this, just line everything up appropriately following the steps I gave you beforehand. And so if we're given the mass of our sample, we can convert our masses into moles using the molar mass. Once we have the moles of each of those elements, we can use the number of moles as the subscripts and then change them by however we need to go by to get a simple whole number ratio. And once we have the empirical formula, we can figure out the empirical formula's mass. And we are given the molecular mass, I tell you, is 90.09. So if we can determine the relationship between this mass and the empirical formula's mass, we can use that same relationship between the empirical formula and the molecular formula, like such. And so, we start off with 40 grams of carbon, convert grams into moles using the molar mass of carbon to get 3.33 moles of carbon. Or 6.71 grams of hydrogen, using the molar mass of hydrogen, we calculated 6.66 moles of hydrogen. And similarly, with our 53.3 grams of oxygen, use the molar mass to calculate 3.33 moles of oxygen. And then looking at the relationship between all of those, if we divide all of these by the smallest value, we end up, again, dividing each of them by 3.33, we end up with a empirical formula of C1H2O1, or dropping out those ones because we typically don't write those as subscripts, we end up with CH2O. And so the next thing here is the only thing you can really do at this point with that value is figure out what the mass of that empirical formula is. And so you know the masses because I gave them to you. So 1 carbon plus 3 hydrogens plus 1 oxygen will give you 30.03 grams per mole. Now looking at the relationship between our masses, the mass of our empirical formula is 30.03. The mass of our molecular formula is 90.09. And again, this has to be given to you, and that's the only way you're going to be able to figure out this last step. And so once this value is given to you, now you can figure out the relationship between this mass and that mass. And so plug it into your calculator if necessary, but 90 divided by 30 is 3. Meaning the fact the masses are tied to each other by this number or this multiple of 3. If the masses are tied to each other by 3, that means the formulas must be tied to one another as 3 as well. And so our CH2O now becomes C3H6O3. And a very, very easy way to double check and make sure you didn't mess up somewhere is just to figure out what the actual mass of your C3H6O3 is. If it comes out to what I already told you it has to be is the 90.09, then you're pretty much in the ballpark and probably correct, hopefully correct. And so, if that hasn't scared you enough, let's do another practice. So a dye has a percent composition of 75.90% carbon, 6.38% hydrogen, and 17.72% nitrogen by mass, with a molar mass of about 237.3 grams per mole. And I want you to determine the molecular formula of that dye. And so take it one step at a time, do the 4 common steps that I kind of mentioned. The first one is convert all your percents into masses. I'm not going to write that down because it's a very easy step. Just take all these masses and change them, or percents, and change them into grams. So then the next step is convert our masses into moles. So our 75.90 grams of carbon can be converted into 6.320 moles of carbon. Similarly with the hydrogen, 6.38 grams of hydrogen is 6.317 moles of hydrogen. And last but not least, 17.72 grams of nitrogen comes out to about 1.265 moles of nitrogen. And so in this case, I chose this particular type of problem because you're going to have to give me a little bit of wiggle room whenever you do some of these calculations. And so in this particular problem, our 1.265 is the smallest subscript that we would write in our pseudo formula. And so if you divide all of your values by 1.265, you end up with something very close to 5, something very close to 4.99, and of course, the number 1. And so this 4.99 here, one thing I want to make perfectly clear is you will never find a molecule of something like C500, H499, and 100. That doesn't happen. And so the only way that I can get this to be exactly 5 is if I were to carry out these percentages all the way out to like the 10th decimal place. So that's the only way I'm going to end up with exact numbers for each one of these compounds. And so if I'm off by like maybe like 2/10 or like of a decimal point, then just again do a little bit of rounding. So if you see something like 4.9 or 5.1 or something like that, just take it again for the grain of salt that it has to be a whole number. And so after that, take your take your moles and create them the subscripts. And so our empirical formula would come out to C5H5N. And from there, you can calculate the molar mass of this of 5 times 12.01 plus 5 times 1.01 plus 1 times 14.01 to get 79.11. And now again, we know the empirical formula's mass is 79.11. We know the molecular mass is 237.3. So do some math. 273.3 divided by 79.11 comes up very, very close to 3. So the masses are tied to one another by the value of 3, and that means the molar mass and the molecular formula and the empirical formula must also be tied. So here your C5H5N now becomes C15H15N3. Just do a little quick check, make sure that your C15H15N3 is close to the mass of 237.3, and again, hopefully that works out in your